We've seen that the Schrödinger equation can be easily solved for a system like a free particle when there's no potential. What we want to do now is examine a case where the potential is such that it actually confines the particle to a particular region in space. So this becomes a bound particle instead of a free particle. So in this case, our potential function is going to be equal to a couple of areas. 0 when the coordinate is between, say, 0 and capital L, and it's going to be outside that, it's going to be infinite. So when x is less than 0 or x is greater than L, the box is going to be infinite. So I'm going to draw it way over here to give myself room for other things later on. So we have a box something like this, goes from 0 to L, and the sides here are infinitely high. Now, since there is no potential here in the middle part of the box, this is going to be like a free particle in there. And we already have seen that for a free particle, the wave function has the form a cosine kx plus b sine kx. Okay, so it's just going to be some sort of oscillating function. When we get to a barrier, though, we've seen that at a barrier, the nature of the wave function changes. And in the case of the free particle, if it hit a potential barrier, it moved from becoming an oscillating function into one that was a exponentially decaying function. So in that case, we had a situation where psi of x would be equal to something like a e to the minus kx. And again, k in all of these cases is 1 over h bar square root of 2m e minus v0, or in some cases v0 minus e, depending on which is greater. So if this is the case, we can see that as v0 goes to infinity, which is the case here, these are infinite walls, then this is going as a e to the minus infinity x. All right, then the effect of that is to make it so that the wave function is essentially going to 0. If you raise e to some really large but negative power, that means that this wave function is going to 0. So in other words, this goes to 0 at the walls. Now, what does this mean in a real physical sense? Well, it means that at these walls, the wave function is fixed. So you may recall the vibrating string where we had it fixed to two walls. Is very much the same sort of thing. We're going to have boundary conditions at the walls that require the wave function to be 0 there because the potential becomes infinite. So what does that really mean for our wave function? Okay, well, I'm going to start writing this in red because this is where it's going to get a little bit more important. We're going to have a wave function that's equal to 0 at 0 and also at L. So when I plug that into my general form in the inside of the box, I will have that y of 0 is just equal to a, but that's equal to 0, so therefore a is equal to 0, and our wave function must be b sine of kx. All right, when x is equal to L, then I will have b sine of kl is my wave function. And in this case, again, as in the case of the vibrating string, we saw that this had to be solved by setting kl equal to some integer multiple of pi. Or in other words, k has to be equal to n pi over L. Which means that our wave functions now, and I'll label them with this number n, where n is an integer. These wave functions now must be equal to some constant times sine of n pi x over L in this case. Okay, well, that means that we're going to have functions that look like this, or look like this, or look like this, just as we did for the vibrating string. So these are the same sorts of wave functions that we'll find for this particle in a box system. But one thing we haven't answered, though, is how does this affect the energies that are allowed for this particle? Well, it actually has answered that because we can write k in terms of that energy, as we have done right here. And we have the k in terms of this number n. So all we need to do is to set those pieces equal to each other. So I have n pi over L is equal to k, and k is equal to, and now we have v0 is equal to 0 in this part, so we just have k is equal to 1 over h bar square root of 2m times the energy. So if I square both sides, and now I'm going to ignore the k in the middle here, I'll have n squared pi squared over L squared is equal to 1 over h bar squared times 2m times the energy. And now I might as well label the energy with the same number n because it will vary depending upon the value of n. So now if I rearrange this, En is going to be h bar squared over 2m times n squared pi squared over L squared. But h bar squared, remember h bar was equal to h over 2 pi, so h bar squared is going to be h squared over 4 pi squared. So the pi squareds there would cancel. I'll get a factor of 4 in the denominator. So when I finish working all of this out, I'll end up with a result that looks like this: that the energy levels are equal to h squared n squared over 8m L squared. And that, in fact, is the final result for the energy levels of the particle in a box. So what do we gain from this? Well, one of the things that I hope we notice from this is that these energy levels are now discrete energy levels. This is a general feature of bound systems. So we can say bound systems have discrete levels. They don't have continuous energy levels anymore. They have discrete levels, and in part that is imposed by the fact that we have effective boundary conditions. All right, so this is due to boundary conditions that confine the wave. So in other words, our waves are only going to be able to access continuous energies when they have no constraints on where they go. When we constrain the waves to reside in a particular region of space, then we'll have these discrete energy levels. And we can see that we have an actual explicit formula for these in terms of a number n. We will grow to call these numbers n because they'll appear in a lot of these quantum systems. We'll call them quantum numbers. And I have used it to label the state, and this is a completely typical way of handling this. We can label the state with these quantum numbers because they basically set the energy levels according to this functional form. So this is the particle in a box system. It's a particularly convenient system for us to use because it demonstrates a lot of features of quantum mechanics. We see the increasing nodes as we go to higher energy states. The wavelength gets shorter as we go to those high energy states. Both of these things are typical of quantum systems, but also we have very easy functional forms. So for example, the functional form of the eigenfunctions is an easy function for us to deal with. So we can do all kinds of calculations to demonstrate quantum mechanical properties using this particular model system. And these sorts of things will be more difficult when we begin to approach realistic systems like atoms.